So I wanted to come back and look at another wave and to do a Fourier analysis on it. This time it's going to be a duty cycle or pulse width modulation, however you want to describe that. But let's say that we have a wave, and we'll say that we have some VM here, and it's going to then drop down at the quarter point and be off for 3/4, and then back up, and then back down. So we'd have 0, and then t over 4, and t over 2, and then of course 1 period t again. So this is our function v of t, and there's our time t. So we'd like to do that. We talked a little bit about this in terms of controlling speed in a DC circuit or something like this. You might have a wave that looked like this one, where you had the majority of the time was off, or you might have another wave where you have much more time on. And if you're driving a bulb or a light, you'd have in the second case more intensity, brighter light, or faster fan speed, or something like that. So a good wave to think about. So let's see if we can come up with the Fourier series for this thing. What kind of symmetry do we have here? It's not even or odd, is it? I mean, it would continue this way like that, wouldn't it? So it's not even or odd. I don't think it's even half, is it? I'm not sure about 8, so that goes beyond this class. So I don't think it has any symmetry. It has no symmetry that we've talked about, so we can just grind through this thing. So we could talk about an average value. Well, it's t over 2, a half. Yeah. It's not perfectly to scale. So I need to find the average value. We could say that that's equal to 1 over t times the integral from t0 to t0 plus t of f of t dt. Which, I mean, if you like integration, you could do that, or you could just think about the average value. What are we going to do? We're going to sum this up as VM. I mean, if I wanted to find the total area there, that would be VM times t over 4, and then I have to divide by the entire period. So VM divided by 4. Does that make sense for the average value? I mean, you could go through the integration if you wanted to. The other terms, we're going to have to go through the integration, so we'll get some practice there. If we talk about a sub n or a sub k, I'll do it as a sub k, be consistent with your author. We're going to have, 2 over t times the integral from t0 to t0 plus t of f of t cosine k, was it cosine k omega not t dt. So we end up with something that looks like this, 2 over t, and then I have to break this thing up, don't I? I'm going to go from 0 to t over 4, and that function is Vm times the cosine of k omega naught t dt, and I have to add that then to the integral from t over 4 to t of 0 cosine k omega naught t dt, which this second part turns out to be what, 0? We recognize that right off as 0. So if I go through this and do the integration, I have what, 2 Vm divided by t times, I'm going to have the sine of k omega naught t over k omega naught evaluated at 0 and t over 4. That's an easy one because I mean, it's just the integral of cosine, isn't it? The Vm comes out as a constant. So that'll look something like this. 2 Vm over t. Then I'm going to, when I put in the upper limit, I have the sine of k times omega naught, which is 2 pi over t, times t, which is going to be t over 4. And we're going to divide this by k and omega naught. I won't worry about substituting into that one quite yet. And I have to then subtract the sine of 0, right? So what do we end up with? Let's see, sine of 0 is 0, right? And what's this thing turn out to be? We're going to have the sine of, I get to cancel the t's, I have pi over 2, don't I? So k pi over 2. So if I look at the unit circle on that one, and k is all the integers, positive integers, isn't it? So when k is equal to 1, I'm at pi over 2, so I'm right there. Then when k is equal to 2, I'm right there. And when k is equal to 3, I'm right there. When k is equal to 4, I'm right there. That one, I think, I don't want to, that's all over the place, isn't it? In terms of +1, -1, and 0. So I think I'll just leave this as the reduced form. So I'm going to say that I have 2 Vm sine k pi over 2. And then I'll have this k here, and I have, what, 2 pi, and I'll have a t up here in the numerator. So you get to cancel that with that, and that with that. And we come up then with a sub k being equal to Vm divided by k times pi times the sine of k pi over 2. So that's probably good enough for now. So we'll hang on to that. We'll hang on to this average answer. I think I have enough space left here to try b sub k. Yeah.
I've got a couple of questions about setting that.
Okay.
So the reason in that first equation where it's up there, the reason we did 2 over t is because we do 1 over period, correct?
Yeah, this is the, if you look at the standard form where it talks about the coefficients, that's that equation. Okay, if we didn't recognize any symmetry or anything, a sub k would always be 2 over t.
It would always be.
Mm-hmm.
Oh, right, we have that. And so the reason that you did it from 0 to 2 pi over 4, and then, or to t over 4, and then from t over 4 to t was because
You have a discontinuity in your function.
right, so you had to account for slope.
Yeah. So, I mean, this function here is Vm, and this function here is 0. So you had to break it up. Okay? Yes?
Second line from the top,
Mm-hmm.
inside your square brackets that are all the way to the right.
Here?
Yeah.
Okay.
That t that you crossed out.
This,
there.
uh-huh.
Where's that t?
That came from, it was in the denominator of this guy, because we had this omega naught here.
Oh, okay. And then make
Yeah. Omega naught was 2 pi over t, so the denominator of a denominator became a numerator. And then I put it in parentheses because I didn't want to get it in the argument of sine. So it's a little sloppy in my writing there, probably. Other questions? Good to go? We'll get to do it basically over again, a little different trig function, but looking at b sub k, we know that that is equal to, and again it's 2 over t, that's just the given from Fourier. 0 to t over 4 of Vm sine now of k omega naught t dt, and then I'm going to add to this. I'm doing this a little bit differently. I guess the square bracket there. This will go from t over 4 to t of 0 dt. I've run out of space, and I won't waste your time writing the sign since that one is 0. This whole thing's going to go to 0. We've got then b sub k is equal to 2, bring the Vm out, like we did before, divided by the period t, times what are we going to have in here? Minus cosine of k omega naught t divided by k omega naught. I'm evaluating this at, this is going to be what, t over 4 and 0. Yeah, so I have, it's a good way to do that. Yeah, I can just do this 2Vm over t. So when I put this in here, minus cosine of k, what's that turn out to be when you put t over 4 in there? You get something that looks like that with cosine, don't you? Cosine of k pi over 2 divided by k omega naught. And then we're going to subtract a negative, so it's actually adding cosine of 0 divided by k omega naught. So k pi over 2, if I'm looking at this point here, and that point there, and that point there, and that point there as we go around, that's all over the board, isn't it? So, I think I can say that this is, but what about the cosine of 0? What's that? 1. Okay, so this piece here becomes 1. And I could actually factor that k omega naught out, so let me do that. I have 2 Vm divided by period t times k omega naught times 1 minus cosine k pi over 2, which would be equal to 2Vm divided by t times k times omega naught would be 2 pi over t, so I'll put the t up there. 1 minus cosine k pi over 2. So I could say finally that b sub k was equal to, I get to cancel that and that and that. So I have Vm divided by k pi, and instead of just having a sine term, I've got this combination 1 minus cosine k pi over 2. So I've got my b sub k, I've got my a sub k, and I've got my average value right there. So I should be able to put those together, right? Questions before we head that way? So we know we're going to, in general, what was our expression for the Fourier? F of t is equal to a sub v plus the sum n equals 1, 2, 3, and so on to infinity of a sub n times the sine of n omega naught t plus b sub n times the, did I get that right? I think I've messed up cosine and sine, haven't I?
Yeah. You also
And
have that
what's that? Oh yeah, I'll switch to n when I get in here, so I'm not too worried about that. But this should be cosine here, shouldn't it? Yeah, cosine. And the n omega naught t is okay. So I've got cosine b sub n times n sine n omega naught t. So we can say that our function v of t is equal to the average value, which was Vm over 4 plus some n equals 1, 2, 3, and so on up to infinity of a sub n or a sub k, which is going to be v sub m over k pi times the sine of k pi over 2 times the cosine of n omega naught t plus b sub n, which was v sub, now I've messed up with the k, haven't I? Yeah, I want to get these into n, so this would be a n, and this would be an n. A lot going on in this one. There's an n, there's an n, and omega naught t plus v sub m over n pi times the 1 minus cosine of n pi over 2 times now sine of n omega naught t. Oh, we could. I mean, I don't know that there's a lot of simplification to be done. We've got Vm over 4. What could we factor out of here? Looks like we've got a Vm term there, a Vm term there. We got to leave the n's in there, but we could take out a pi. So we could add to this Vm divided by pi times the sum n equals 1, 2, 3, and so on up to infinity of 1 over n. I can factor that out, but I can't take it out of the summation, times the sine of n pi over 2 times the cosine of n omega naught t plus, maybe I'll write this a little differently, sine of n omega naught t times, then we've got those out of there, 1 minus cosine n pi over 2. So you could multiply that through if you want to. I don't think I will. I think I'll leave it like that. So the expressions can get kind of ugly. Let's see how that one works. If you go to on the web page, and then I think the subfolder is the Fourier demo. And we're going to be looking at demo 3. That's a MATLAB. And also a demo 2, that's Excel. Okay, so we'll go and look at these two. And that's where you'd find them on the web page. Let's head there. So this one is probably a little bit small to see, but you can go get the file off the website. Looks like we're going to do an n max of 100. So n is equal to 100, so 1, 2, 3, and so on, up to 100. Okay. And we go through a loop structure. You can see the loop structure there when you look that up. And the output's a little bit easier to see here. So we got something like that. Is that what we started with? I mean, if we said the amplitude was 10, Vm is equal to 10, there's 0, right? That's not too bad. That looks like what we've got. We obviously have a little bit of overshooting and some noise, but that's not too bad. We could remember that n is equal to 100 on this. It wouldn't take much computational power to go to 1,000 or 10,000. I think that would settle right down. So once you get that, you can take this expression. And your labs 4 and 5 talk a lot about doing this, coming up with a way to model things like this, a square wave and so forth, and a square wave that's gone through a filter. So we just take that, and that's going to be our equation inside this loop structure. For you programmers out there, we've got a couple of loop structures here. We have the loop for the time, and we also have the loop for n. You can look at that if you want to. So then this one was the one that was Excel. This was Demo 2 out of Excel. And looking at this, it looks pretty good. Here I've taken the amplitude as 1 rather than 10, and I still have n equal to 100. So I got a little rounding off there. If you went to 1,000, probably be a lot better, but take more time. So if you don't want to have to do the programming in MATLAB, you can do it with Excel pretty easily. So those are both there to help you. You may want to look at those also with an eye towards taking something like that and helping you with labs 4 and 5. Questions with that? Let's try another one. So this time, instead of just our emphasis is not necessarily going to be doing the Fourier for the wave, but now starting to take that series and putting it into some sort of a circuit. So we're going to have a wave like this. So we'll call this V sub g. We'll say it goes up from Vm to minus Vm. This would then be one period here, of course. We'll clear around to another period, 2t. So we're going to feed this thing into this circuit. We'll start fairly easy. We'll get more complicated. So V sub g is going to go in here. We'll have some resistor R and a capacitor like this, and across here we've got our output V0. Okay. So we're going to come up with a Fourier series for the input wave, put it into this thing, and we'd like to come up with the series that we get on that for the output. That's going to be our task. So let's see. A couple ways looking at this wave. It's a square wave, so we could look it up in a table, right? And if you go to a math table or Google a Fourier table or something like that. I think in GE 103 last year you had a square wave, so you could see that the f of t boils down to 4 times the amplitude divided by pi times the sum, n equals 1, 3, 5, and so on to infinity of 1 over n times the sine of n omega naught t. Or if you wanted to, you could grind through this. It doesn't take very long if you recognize symmetry. What kind of symmetry does it have? You sure? Maybe I need to draw the rest of it. Yeah, we've got odd for sure. Okay. Yeah, I always say quarter. Okay, so odd quarter, that's good enough for me. If you use odd quarter, you recognize that the average value is equal to 0, that a sub k is equal to 0, and that b sub k is equal to what? 8 over t times the integral from 0 to t over 4, which should work pretty well for us. And then we put our function in there. What's our function? I mean, over the quarter period, the function is just Vm, isn't it? So I'd have Vm times the sine of k omega naught t dt, and this is for odd k. So this turns out to be what? 8 Vm divided by t. Then you're going to have the integral of sine, so you end up with this minus cosine of k omega naught t divided by k omega naught. Evaluating that as 0 and t over 4. So that turns out to be what? 8 over Vm, or 8 times Vm divided by t. Then I could factor out this k omega naught, so I'm going to have k and 2 pi, and then I will have a t up there. And then I've got minus the cosine of k times 2 pi over t times t over 4, minus a minus is a positive, the cosine of 0, right? So I get to cancel those. I get to cancel that with all of those. So I'm left here with minus cosine of k pi over 2, right? And if we go look at our unit circle on this thing, I think in the last problem we had that, and it was kind of to throw our hands up. We couldn't go much further. But remember, this is what? Odd. So k is 1, 3, 5, and so on. So when I look at 1k, so 1 pi over 2 puts me right here, doesn't it? And then 3 pi over 2 is going to put me right there. And 5 pi over 2 is going to put me back up there, isn't it? So this thing then ends up equaling what? 0. Okay, and what's cosine of 0 then? Yeah, hopefully this amounts to something or I'm going to have a problem. So that's 1. So really that whole thing inside the square brackets is just 1. And I'm left with b sub k being equal to, let's see, to cancel those t's, this is 4, cancels with that. So I have 4 Vm divided by pi k. So I should be able to say that this is Vg is going to be the average value plus the sum, 1, 3, 5 up to infinity of 4 Vm divided by pi k times what? That's the B term, so that would be times sine, wouldn't it? I've got, I made the same mistake. I should be calling this N at this point. So I've got what? Sine of N omega naught T, is that right? So can I get this to look like this thing? I hope. 4 times Vm, that's the amplitude, divided by pi times the sum. I have to leave n in there, so I have 1 over n sine n omega naught t. So we're okay with that. So certainly on the exam in a little over a week, there'll be some problems where you'll be given some functions and you're asked to derive those. And even if you have the most comprehensive table, I don't want you looking the value up in a table. But having said that, you probably want to have some table for some pretty common ones, because even with this one that's pretty easy, it's probably quicker just to look up the form, right? Yes?
So when we put a table, that box,
Uh-huh.
that is going to be our final end product.
Right.
That's the form that we're looking at.
Yeah, because we could use this. I mean, if we put this in there, f of t, that goes to v of g, or v of g of t, right? And then I've got 4. What's our amplitude? Vm, divided by pi times the sum, 1, 3, 5, and so on, up to infinity of 1 over n times the sine of n omega naught t. Do we get the same thing? Yeah, exactly.
And the function we're getting corresponds to that shape of the graph that looks like that.
Yeah, if you were to, I don't have an example done, but if you do use MATLAB on that or Excel, pull up one of the demos that I had and change the function to that, you should get something very much like a square wave.
So
and I mean,
it's a square wave, right? Not odd and 1/4 symmetry. Doesn't correspond to the symmetry, it corresponds to this square.
yes. If you use this equation here or this one down here, they're the same, and plot it, you're going to get a square wave. And you actually did this in GE 103. I just gave you the equation. Okay, so you could go back and look at that if you wanted to. That's still up on the website. So we're not even half done, are we? This is the input. This is what's going in here. So we need to come up with a transfer function for this circuit. If I want to look at the transfer function on this, and I think I have enough room to do the transfer function on this. This is what going to be 6. So basically the transfer function is to say that V naught is equal to what? Well, if I write it in phasor form, I'm going to have this output voltage V naught. By voltage division, I could say that that was VG, writing that in phasor form, times the capacitance, which is what? Minus J over omega C, divided by, I have to sum those up, right? So I'm going to say that that's R plus a minus J over omega C. Everyone okay with that? So then if I want to kind of clean this up, because this is going to be where I'm putting this term. That's going in V sub G. I think I'll make life a little bit easier for me. Let me multiply this then by omega C divided by minus J, and omega C divided by minus J. When you go through that, you get your output is equal to the input, V sub G, divided by, we have, turns out to be 1 plus a R omega C divided by a minus J. Is that how that works? I think I'll get that J up in the numerator, so I could really say that this was equal to V sub G divided by 1 plus j omega RC. I think I can say that. So that's kind of nice. That's my transfer function. So there's where I put my input signal. This is the input. And I'm going to take that input and put it right there, and I'll be able to figure out what my output is. So that's what our scheme is. Questions so far? Well, let's see how this plays out. So I'm going to take one of these, either this one or this one, and I think I'll write it in terms of the harmonics. So let me just do this one at the bottom because we can see it a little easier. So I'm going to say that the input signal, this is what's going in, is going to be, I've got 4 Vm divided by pi times the sine, when n is equal to 1, right? I'm going to have 1 over 1, so I'll just have sine of 1 omega naught t, right? So that's with n equals 1. So now n is equal to 3. What do we have? Oh, we're going to have 4 Vm divided by 3 pi. Isn't that what that says? Yep. Times the sine of 3 omega naught t. And I could keep going on this. N is equal to 5. So I get 4 Vm divided by 5 pi sine of 5 omega naught t. And I don't know that we need to go much further. I think you get the point there. So if I put the first function, first term through the transfer function, so I got the transfer function right here. So I'm going to put that first one in. What does this one look like in phasor form? If I write this in terms of a phasor, nope, just this term right here. And one thing I'm going to do is I'm going to write it in terms of sine. Normally we write it in terms of cosine, but I can write it in terms of sine. I just have to be careful at the end and realize that I wrote it in terms of sine. If I think about this in terms of sine, can I write this as a phasor for Vm divided by pi at an angle of 0? Are you by that? And what would this one look like? For Vm divided by 3 pi at an angle of what? 0? Yeah, there's no phase shift there. And we could just keep going with that. Okay. So what I'm going to do is I'm going to then put that into the transfer function. So I'm going to say my output now for the first harmonic is equal to what? I take this 4 Vm at an angle of 0 divided by pi. That's the numerator of this thing. Okay. And then I have to divide that by what? 1 plus j. And here I have to be very careful because we said that this was j omega RC. I need to at some point recognize that this is going to be n omega naught, right? Because that capacitor is going to change with the frequency change. So I've got j n omega naught. So let's see, when n is equal to 1, I would just have omega naught times RC, right? So what's that look like? Maybe I'll write that below. I could say that this was 4 Vm over pi. Then I need to put this denominator in terms of a magnitude. I'd have the square root of what? 1 plus omega naught squared r squared c squared. And does this thing have an angle? Yeah. The angle is going to be 0 minus the angle of the denominator. The angle of the denominator then is the arctangent of the imaginary portion, omega naught RC, divided by 1. Okay.
And that's where the J went in the magnitude.
Well, remember that when we do the magnitude, we go to the real and the imaginary, and we went out there. The real is 1, and then I'm going to say that's a positive number. It will be a positive number. There would be, this is in the j direction. There's the omega naught RC, right? And we are quite literally using the Pythagorean theorem and finding that diagonal distance. Other questions? So let's try this for the second term. So what's the second term going to look like? Which is when n is equal to 3, right? So I'm going to have 4 Vm divided by what? 3 pi at an angle of 0. And then I have to divide that by what? 1 plus j. And here's where I have to be careful. There's an n in there, right? Here, right there, n was equal to 1, wasn't it? But here, n is going to be equal to 3. So I'm going to have 3 omega naught RC. So when I come down and continue working on this, this becomes what? 4 Vm divided by 3 pi times the square root of 1 plus, what's that going to be? 3 squared, which will be 9, omega naught squared, r squared, c squared. And this is going to be at an angle then of minus the arctangent of what? 3 omega naught RC.
And that's just, it's a negative arctangent because of the capacitor, right?
That's a negative arctangent because it was in the denominator.
Oh, right, the angle of...
Yeah, the angle in the numerator is 0, so I really have 0 minus the angle of the denominator.
So when did we get an n attached to the j?
Well, when we did our transfer function, we came up with this where we had 1 plus j omega RC. And we need to recognize that that omega is going to change. It's going to be n times omega naught. Because the transfer function isn't going to stay the same as the frequency changes.
Yeah, so as the way series goes out.
Okay. So I substituted from this omega, I substituted n times omega naught. Okay. Well, let's do one more, and then maybe we can make the transition. What are we going to have here? 4 Vm divided by 5 pi at an angle of 0, and then we're dividing this thing by 1 plus j 5 omega naught RC. This will be 4 Vm divided by 5 pi. I'm going to have the square root of 1 plus 25 omega naught squared r squared c squared, and we have then minus the arctangent of 5 omega naught RC. And of course this continues on. So I think at that point, and you once you get used to this, you probably can just do it with one term, but we should be able to say then V naught t putting this back into a Fourier series, what's that going to look like? How could I write this with a summation sign? Well, it looks like I got 4 Vm over pi, right? Well, the n's got to go, you're right, n. I mean, this is, n is equal to 1 here. So you're absolutely right, we have an n, but that's got to go inside the summation. So I'm going to have 4 Vm divided by pi. Then I have the sum, 1, 3, 5, and so on, up to infinity of, there's the n. We don't want to forget that. And we also have this radical that's always hanging around in the denominator. What's that? 1 plus, I could say n omega naught rc, that's all squared. And then what do I have in the numerator? Yeah, but I want to write this not in phasor form. I want to go back into a form that looks like this. So remember, I wrote this in terms of sine, so I'm going to go back in terms of a sine. So I'm going to have sine. I guess I probably don't need the e on sine. Okay. So I've got sine. What are we going to have? N omega naught t, is that right? I don't want to end that yet. I've got a phase shift. I haven't taken into account this phase shift. What's that phase shift going to be? Minus the arctangent of n omega naught rc, right? Isn't that what you'd have? I think so. So a lot of steps in there, a lot of tedium in there and whatnot. Fairly easy problem. We're going to do more and more difficult problems. But, you know, like anything, it seems kind of hard when you do it for the first time, and then it gets easier and easier. Yes?
Just on that last equation, inside the angle of sine, we wrote it as n omega naught t, but really it would still be 0 all the time.
Would be 0.
Because n is all numbers in sine.
Well, no, I don't think it'd be 0, because, for instance, this one, I mean, we're just going back to the time domain. With these, I'd convert it to the phasor domain, and then this,
So it's only 0.
Yeah, and the phasor, this is in the phasor domain, and then this one is in the phasor domain with the magnitude, and then I went back to the time domain. Other questions? Let me double check my conclusion there, make sure I haven't pedaled off something that's got a typo or mistake in it. No, I think we're good. So this is what we would get for the output. You could go ahead and plot that and see how that would work. Be kind of interesting. You put a square wave in, and then this is the wave that you get out. It's gonna have a phase shift. I find that kind of interesting. Not only changes the amplitude, but also shifts the phase a little bit. Well, the last problem that we'll do for today, well, it won't be quite as involved as this, but it's going to be a little different way to look at things. So let's say that I have a Fourier series representation. I have some voltage that's equal to the sum n equals 1, 3, 5, and so on up to infinity. And then I have this 20 divided by n pi times the sine of n omega naught t minus 40 times the n squared pi squared times the cosine of n omega naught t. Yeah. And what I'd like to do is I'd like to write the first four terms in the in phasor form, what sometimes they call the phase spectrum or phasor spectrum. So this is actually a representation of a wave that looks like this. We look this up in a table, but we'll do something like this. Back again. Okay, I don't know that we need to know that, but just looking at that, let me double check, make sure I haven't written this wrong. I think we're good. Okay, well last time we had it fairly easy. We had a sine and everything was in terms of sine, so I said, hey, I'm going to write my phasors in terms of sine, and then you'll notice at the end when I turned back to phasor, I didn't go to a cosine, I went to sine. I would have been off by 90 degrees if I'd written a cosine there. This one is a bit more problematic because I have sines and cosines mixed. So I'd better get consistent here. I could change this cosine to sine, but since we're probably a little more used to writing cosine, let's change the sine to cosine. So I'm going to say that this is equal to the sum 1, 3, 5, and so on to infinity now of 20 over n pi times the cosine of n omega naught t minus 90, and that's in degrees, so I have to be careful of that, minus 40 over n squared pi squared times the cosine of n omega naught t. So let's see. When n is equal to 1, what are we going to have? What does this look like? 20 divided by pi times the cosine. Our phase shift here is what, minus 90? Is that how I write that? Put that in phasor form? And then I'm going to have to subtract off 40 divided by pi squared. And we have a 0 phase shift there. So we could say this is equal to 20 over pi, turns out to be about, what, 6.3662, I think is what I calculated at minus 90. Then I have minus 40 over pi squared is going to be, pi squared is about 10, so it would be about 4.053, pretty close to 10, at an angle of 0. So maybe I'll line these up. You get done with this, you have a 7.55 at an angle of minus 122. So that's what you come up with. So let's talk about when n is equal to 3. What's this thing look like? What are we going to have? Well, no, I've just converted it into the. I mean, this is in time domain, right? So this is phase. Okay. So let's see, what am I going to get here? I'm going to have, when n is equal to 3, I have 20 divided by 3 pi at an angle of minus 90. And then I have to subtract off, 40 over 9 pi squared at an angle of 0. So I have to, I don't think I have those. So I have 2.12 at an angle of minus 90 minus 0.450 at an angle of 0. So we end up with 2.17 at an angle of minus 101.9, let's say minus 102. Mm-hmm.
So when we're placing any angle through, we get to things like cosine towards n omega naught t.
Mm-hmm.
Where does the n omega naught t go?
Well, remember this is in the time domain, right? So if you take this in the time domain, and you want to write that now in the phasor domain, what does that look like in phasor domain? Going to be some magnitude at minus 90, right? The magnitude is this piece here. Okay. So are you essentially? I mean, to get from here, we're using Euler's equation, right? This isn't magical. It's the same thing we started out last term with. Good question.
Did you convert it? Are you converting it from the time domain to the phase?
Oh, yeah, absolutely.
By using the triangle.
Well, I'm using Euler's equation. Just like last. What do we have? Last term, we might have had a number that was 36 cosine of 377 t plus 30 degrees. I mean, you came up with a v of t like that. We saw something like that all the time last term, didn't we? Okay, so in phasor form, we have 36 at what? 30? Okay, and from here to there, that was again Euler's, wasn't it?
So basically, by changing n this new form, when we go through Euler's equation, that's something in the final magnitude.
Right, it's going to change the transfer function, but it's not showing up here.
Okay, that's where I was a little.
So let's see. I don't know did I say 3 or 4 terms? We'll do one more term. So we'll do n is equal to 5. So that would be what, 20 divided by 5 pi at minus 90 minus 40 over 25 pi squared at 0. So 1.27 at an angle of minus 90 minus 0.16 2 at an angle of 0, which is really just an angle of 0 is a real number, right? So what do we have? (1.28) at minus 97.3. And it's probably not a bad way to think about this, because we could really think of the input signal as being this sum of voltage sources. Let's say I wanted to model the first 3 terms going into something. I could think of it really just as these sources here, where this is this one, that's that one, and that's that one, right? Yeah. So you're just going to put those in. The other thing that's very interesting is as the frequency, as the n terms get higher, what happens to the size of the terms? They get much smaller, don't they? There's a phase shift. The phase shift gets smaller, but the magnitude gets smaller too. So what we'll do then with this, are there questions with this? We got this pretty well set? Okay. Just a little different way of looking at things. What we'll do next time is we're going to take that and we'll take those terms and we're going to feed them into a filter circuit. We're going to make our filter circuit quite a bit more complicated than the last one. We'll have a resistor here and a cap there, the resistor here and a resistor there. Okay, and this is going to be our out, and this is going to be the in. So we'll go ahead and take what's represented by this, feed that into there, and we'll see what we get on the output of it. So that'll be a pretty good challenge. So make sure you keep your notes handy with this, because this will be our starting point for that. We'll go from there. Questions? That's where we'll head next time. Take care.